chapter 21 is about current electricity. Prior to this, we were talking about static electricity, and static electricity just sort of sits on insulators or sits on conductors. In 1800, a man named Alessandro Volta discovered that different metals could be used kind of like in layers to create the first battery. They called it actually a voltaic pile. And I don't want to spend a lot of time explaining how a battery works, but I'd really like you to read chapter 21, and that first section is going to give you a pretty good idea. Now, most of the batteries that you guys go to the store and buy are 1.5 volt batteries. AA batteries, AAA batteries, C cells, or D cells, even though they're different sizes, they actually are all 1.5 volt batteries. Now, they do make some others. You can buy that kind of boxy square 9 volt battery, the one that crazy kids will stick on their tongue and they'll feel a shock. Don't do that, but that's a 9 volt. Or they make some rather bigger, boxier land batteries. Those are 6 volt. They're actually just a combination of 4 1.5 volt batteries. But most of the batteries that you buy, whether it's for your flashlights or your calculators, are 1.5 volts. AAA's really small. AA's a little bigger. D cells are those big chunky ones that you see. The difference being is a D cell, which is about that big, is going to hold a whole lot, well, with a diameter about that big, it's going to hold a whole lot more chemicals in it than, say, a AAA battery that you're going to put in your calculator. So one reason that some of the batteries are a lot larger, simply so they can hold more of the chemicals that are used. Okay. Now, when we connect a battery, we need to be careful on how we connect it. If we were in the lab, we could actually practice this and measure, but we're not, so I'm going to just explain. When you connect things in series, it looks like this. Generally, when you think of series, just think of one big loop. There's only one current path when you wire something in series. So we might have a battery. The positive end always has that little bump on it. Okay. When we connect them in series, there's a little bump again. We just make them actually touch, and you'll see basically here they're touching. It's that little bump here, and this one touches there. Okay. When we connect them in series, we have to connect from here, from positive to negative. If this is 1.5 volts and this is 1.5 volts, that's going to give us a total of 3 volts. Basically, what it's saying is when charge flows to the battery, it gains energy. 1 coulomb is going to gain 1.5 joules of energy and then gain another 1.5 joules. So in total, a coulomb of charge flowing through both batteries is going to gain 3 joules of energy. That's the correct way to wire in series. This is the wrong way. There's really 2 wrong ways. If I take 2 batteries, and then we're going to let them touch. We're not going to worry. And I do minus, plus, then plus, minus. That's even though this is 1.5 volts and this is 1.5 volts, this is basically going to gain 1.5 joules, then lose 1.5 joules. This gives us a total of 0 volts. Okay. You cannot connect them like that and use them in a circuit. Okay. Now, the whole purpose of this, of course, is to do something. Let's suppose we have this in a light bulb or something, and we connect it to a little light bulb. And light bulb connections, usually there's a little point on the end, something like that, and then another contact point over on the side. And that will make the bulb glow. Notice there's really just one loop for current. All of the current goes through the first battery, through the second battery, all of the current flows, and you can't really see it, but it flows up in here through this little filament and back out. But there's only one current path. Okay. The other way you can connect batteries is side by side. And when we connect the batteries where they're side by side, that's called a parallel connection. Think of it as being side by side. Now, when you have a parallel circuit of any kind, one of the things we're going to find is there's actually not just one current path. There's usually at least two current paths, and sometimes there can be more. Now, when we do this with batteries, here is the correct way. Take your battery, plus, minus, and here's that little bump if you want, and here's another battery, plus, minus, and you connect these two ends together. Now, that seems like we're doing it the wrong way, but it won't be. And these two ends together, and now we can connect them and light up our light or whatever we're trying to do. There's our light bulb. Now, when we connect them side by side, this potential difference is only 1.5 volts. We don't get 3 volts. We're not adding them together like we do when they're in series. In this way, it's sort of like having two horses side by side working together. They're not like horses, but they're doing the same thing. The advantage in wiring something in parallel is simply, it's like having a spare gas tank. The chemicals inside the battery will last longer because you're still only using 1.5 volts, okay? So you can picture the current flowing through the battery still, but when it goes around here, some of the current flows through this 1.5 volt, and some of the current flows through this 1.5. So the current literally splits and comes back together. So this battery is providing half the current, and this battery is providing half the current. It'll still light up the bulb, but not as bright as 3 volts. The two that are wired in series will make that bulb glow brighter. However, they'll also run down the battery quicker. Here we won't be as bright, but it will last a good bit longer. Okay, so this doesn't increase the voltage when we do it in parallel. It doesn't make things glow brighter. It does make the batteries last long. When we had it in series, they actually added together to make 3 volts, and the light bulb actually glowed much brighter. Now, one of the things that we know is that in order to have an electric circuit, we have to have a closed path, a complete circuit. If we don't have if there's a break anywhere, or if we open up a switch anywhere, current won't flow, okay? The best analogy we have really for how electricity works is water. What water does is really very similar to what electricity is. So let's picture a water fountain, like you would see in a park or a garden, and I'm going to put the spout kind of big for a reason. So here's a fountain sitting out in a park. We got a basin full of water, something nice and artistic. There we go. And water, we use blue for the water, is being shot up and it falls back down into the basin. Now, everybody understands, we'll draw some more water in here. Everybody understands why the water falls. The water falls because of gravity. Then the water naturally falls from high gravitational potential energy, to low gravitational potential energy. So the part about the water droplets falling makes perfect sense. We understand that. The real question is, if this fountain runs continuously and we're recycling this water that's in this basin, why does the water go back up out the fountain? Why does it shoot out? Something has to do work on that water to make that happen. Usually what we use is a water pump. Okay. The water pump does work on the water to force it out the top. In other words, the water pump takes it from low gravitational potential back up to high gravitational potential. Another way you can think about it is that it creates the water pressure that causes the water to shoot out. So in order to keep this water flowing continuously in a cycle, it's not enough that the water droplets will naturally fall from high to low. We got to have some way of forcing the water back up from low to high, and that's the job of the water pump. Okay, if we're talking about electricity, that's the job of a battery. Okay, a battery takes electric charge from low potential to high potential. So here's my battery. There's the positive side, there's the negative. The positive side is generally considered to be high electric potential energy, and the negative side is considered to be low electric potential energy. Sometimes we think of it almost as being, if this is a 1.5 volt battery, 0 volts to 1.5 volts. Okay, we connect this to a piece of wire. Make my wire nice and thick this time. And that wire is connected to, we'll put a little light bulb there or something. And then back around to the battery. Now, if this is high electric potential energy and this is low, what we know is electric charge wants to naturally fall from high potential to low potential. So we can think of little positive charges flowing out of the top from this end and traveling through. Why do they go this way? Well, they want to get back, and they're going to actually go up in here, through the filament, back out. But they're trying to get back to low potential. And then when they go into the battery is like a pump. And it takes that positive charge and it takes it and it moves it from low electric potential energy back up to high. The battery actually is doing work on the charge because you don't go from low potential to high potential naturally. If I took this marker cap that's in my hand, it won't naturally go from low gravitational potential energy up to high. But if I drop it, it will naturally go from high down to low. Okay? So our battery is like that water pump. A lot of times people think that the battery supplies electrical pressure. It pushes all the current, pushes on those charges so they flow. And an interesting thing is when charge flows, it all flows simultaneously. The charge, it's not like it leaves here and builds up in some places. The charge either is all moving or it's not. If I were to suddenly break this wire, all of the charge would stop moving. But as long as it's a complete circuit, and as long as we have a good battery that can maintain that electric pressure, it'll flow. Now there's only one thing wrong with this picture. It's not wrong, I did it correctly, but unusual. When Ben Franklin started using the terms positive and negative to describe electric charge, we didn't know very much about the structure of the atom, and we didn't know very much about electricity. Well, he decided that, or somebody, whether it was him or someone else, that we would consider the flow of electricity or current to be the flow of positive charge. So we defined current as the flow of positive charge. And so this is what their picture looked like. And this is still how we define current. This blue positive flow is what we call conventional current. Now, there's only one thing we really need to stop and think about is, after they began to understand the atom, we learned that the positive charges are actually trapped inside the nucleus. Positive charges, so if I have a piece of copper wire, let's say this is a piece of copper wire, it's made up of copper atoms, and the positive charges are trapped inside the nucleus. They don't actually flow. The thing that actually flows are the electrons. It's those electrons on the outer shell that are flowing. So even though we call this conventional current, and we say the direction of the current will be considered out of the positive, there's our current, and it flows back down and into the negative, we now know that what really happens is the negative electrons are what's moving. So even though this is our picture of what's going on, what's actually happening is negative charges are going in the opposite direction. Now, the nice part is, mathematically, a clockwise flow of positive charge is identical to a counterclockwise flow of negative charge. So even though we act like positive charge is flowing clockwise, what's actually moving are electrons, and they're going counterclockwise. We don't have to worry about that. It doesn't change any of the math. It doesn't really change any of our thinking. But it's important to understand that in a conductor, it's electrons that are moving. It's not actually positive charges. Now, in solutions like salt water, where you have both positive and negative ions, both the positive ions and the negative ions can flow. So there are times where positive charges can flow, but the protons inside the nucleus of an atom cannot flow. Okay, now, so let's go back, let's keep thinking. So what we know is that batteries, in the book a lot of times they're using the word cells for the battery. They're called dry cells, although they're not really completely dry. If you were to cut, the original batteries were wet, but now they use a paste, so they're much drier, but they're not completely dry. Batteries do work on electric charge. Okay. We describe them by something called their voltage or their potential difference. A 9-volt battery does 9 joules of work coulomb of charge. Okay. A 12-volt battery does 12 joules of work on every 1 coulomb of charge. In general, we know that 1 volt is equal to 1 joule per coulomb. Remember, coulomb is our unit for measuring electric charge. Okay, so we've talked about 2 important ideas. We've talked about what a voltage is. That's how we measure batteries. It tells us how much electrical pressure is in that circuit. And we've talked about the idea of current. And we'll come back to current, but just so you know, current is usually measured in a unit called amps. Okay. Feel like, let me make sure I have. Yes, let's stop and talk about current a little bit more. Current is the rate at which charge flows we measure current in amperes. 1 ampere, we don't usually say ampere, we usually say amps, is 1 coulomb per second. So if I put a meter right here and I saw that 1 coulomb of charge flowed by that point every second, that would be a charge of 1 amp. If we were doing water, we might measure how many gallons per second went by. But with electric charge, how many coulombs per second? The symbol for current is an I. That's an unusual choice, but we're already using C for other things in physics. And the symbol for current, for amperes, is a capital A. So current, which is represented with a capital I, is measured in amps, which is represented with a capital A. Okay, so that's just some kind of new symbols for you to be familiar with. So we've talked about voltage and we've talked about current. Those are probably the 2 you're most familiar with, but we also need to talk about something called resistance. And the symbol for resistance is a capital R. And this tells us how much a circuit impedes current flow. Well, it makes sense that current will be able to flow through some materials easier than it can flow through others. Generally, all of your metals have very low resistance. Things like glass and paper and string have really high resistance. So that's there. If we think about our model with water, an 8-inch pipe has much less resistance than a 1-inch pipe. You'll have a whole lot more current flow going through a pipe that's this big around, 8 inches across, than one that's about this big, or 1 inch apart, okay? So an 8-inch pipe would have low resistance, and a smaller pipe might have a higher resistance. The same thing is true when we think about wires. Generally speaking, thicker, shorter wires have less resistance. A big, thick cable like they use to run power when they're running it for miles, actually they try to keep that resistance really low. But a big, thick cable is like having a great big pipe for the water to flow through. You have a big pipe for the electricity. A really thin wire is going to have more. Now, generally speaking, wires don't have a lot. If I just take a regular old battery, and I just take a piece of wire that doesn't have anything connected to it, okay? The wire has very little resistance. And quickly drains the battery. In fact, if you're touching this wire, you'll notice it gets really hot because so much current is going to be flowing through it because there's really nothing to slow it down, okay? That's called a short circuit. When you have a piece of wire that's basically directly connected from high to low potential and there's nothing really much there to slow it down, it can get really, really hot really, really quickly. In fact, you can start fires with a short circuit because this wire gets so hot. Now, if I put a light bulb here, there's a little light bulb stand. There's my little light bulb. Whoops. So one end of the wire is connected there, and the other end of the wire is connected here. The light bulb will glow. But generally, bulbs have a high resistance. The light bulb filament has a high enough resistance that the filament gets so hot that it actually glows. But you'll notice the wire doesn't get hot because we don't have a short circuit anymore. Before we might have had huge currents, 9, 10 amps, I don't know. And here we probably just have a few milliamps because this resistor makes it, that little teeny tiny thin light bulb filament makes it really hard for current to flow freely. It impedes it. So this has a higher resistance, slows down the current, and that high resistance is why it glows. Now, if you have something like this in your light bulbs, I don't know if you've ever had a lamp that quit working or you tighten it, it would work and then it wouldn't work. One of the possibilities is that somehow you've got a piece of wire that's bypassing the light bulb. Current is going to take the easiest path. It's going to go, if this is the case, and you have this little piece of wire here, your charge is going to flow like this, and it's going to just bypass that light bulb, and that light bulb's going to go up. Why? Because it's hard for current to flow through the light bulb, and it's easy for current to flow through the wiring. So that's what a true short circuit is. Basically, when you have a short circuit, almost all of the current flows through the short. A piece of regular wire may feel more like an 8-inch water pipe, and a light bulb may feel more like a ½ inch water pipe. Why in the world is it going to take this difficult path through the light bulb, this high resistance light bulb, when it can, this short allows it to just go around, it's like a detour, and totally skip it. But again, the problem with a short circuit is two things are going to happen. One, your light bulb's going to go out, and two, this wire and this battery are going to get really, really hot because they're going to have a really, really large current. All circuits need a certain amount of resistance to keep those current levels safe. I mean, it's just like you wouldn't want your pipes to be wide open so that every time you tried to wash your hands, water came flooding into your bathroom sink like it was out of a fireman hose, right? You don't want that much current. Well, same thing with this. We don't always need that much current. Okay, there's a really important relationship between these quantities. And that important relationship is described by something called Ohm's law. And you'll see Ohm's law written a lot of different ways. I'm going to write it. It doesn't apply to all materials, but it pretty much applies to all conductors. So for our problems we're going to do, it's going to always apply. And it says that the voltage is equal to I times R. And of course, that's voltage. Remember I said I is current. We measure current in amps. We measure voltage in volts. And R is resistance. We measure resistance in a unit called an ohm. And the symbol for an ohm is an omega. And it looks like an upside down horseshoe. It's a Greek letter. So Ohm's law is V equals I times R. One way to really help some students solve problems with it is if we put it in a triangle like this. V over I times, I'm going to put dot R. I times R. The fun part about it, if you can write it that way, it'll help you. If you're trying to find the voltage, you need to multiply I times R. Well, duh, if I want voltage, but what if I'm trying to find the resistance? If I'm trying to find the resistance, if I cover up that R, I need to do V divided by I. If I'm trying to find current, I cover up the current, and I need to do V divided by R. So that'll help you remember which way to use Ohm's law. Looking for voltage, multiply I times R. Looking for current, do voltage divided by R. Looking for resistance, do voltage divided by current. Let's do an example. It says a circuit with a 12-volt battery has 2 amps 12-volt battery and I have 2 amps of current. Well, let's see if we can find the resistance. If I cover up resistance, I see that resistance is voltage over current. R equals V over I. So the answer is going to be 6 ohms. That circuit has 6 ohms of resistance. So different example, suppose that we have a heater and that the resistance of that heater is 9.6 ohms, and we plug it into a 120 volt wall outlet. In the United States, all of our wall outlets are supposed to be around 120 volts, plus or minus 5 volts. It's not, there's a little variation, but that's perfectly all we need. If I want to find current, I'm going to cover up current. I go, oh, current is V over R. (120 volts, 9.6 ohms. That comes out to be 12.5 amps. So Ohm's law is easy to use. I don't think you'll have any trouble with that at all. Okay, let's go. I want to talk about a couple more little things before we stop. Electric power tells us the rate of using or generating electric energy. Power is equal to the voltage times the current. And I don't know if you remember this, but the unit for power is a watt. We measure it in watts. And 1 watt is equal to 1 joule per second. So if you have a 1400 watt blow dryer, it uses 1400 joules a second. If you have a 60 watt light bulb, it uses 60 joules per second. A 40 watt light bulb only uses 40 joules per second. But a 40 watt light bulb won't be as bright. You want it really bright, go get you a 150 watt light bulb. It'll use 150 joules per second. Now, those are the old incandescent light bulbs. When you go shopping now, most of the light bulbs are either LEDs or fluorescents. And if you look close, they'll say things on them like 9 watts, same amount of light as a 60 watt incandescent bulb. So we've really dramatically reduced the amount of energy we're using with those new LEDs and those newer fluorescent bulbs. So power is just voltage times current. So it's easy to calculate. And the amount of energy you actually use is simply equal to the power times the time. But remember, since the power is in watts, that's a joule per second, you need to make sure that T is in seconds. Okay, so power is voltage times current. The amount of energy you actually use or consume is equal to the power times the time. Let's do an example. Let's find the power. If we have a blow dryer, that uses 10 amps 120 volts. Again, most of our households, that's what you get when you plug something in. You get 120 volts, blow dryers drawing 10 amps, and power equals VI. So the voltage is 120, the current is 10, that's 1200 watts. That's a pretty typical blow dryer. They make some that are less, they make some that are a lot more. Microwaves have about similar ratings. A typical microwave is about 1,000 watts, but you can get an 800 watt one, you might get an 1100 or a 1200 watt one. The more wattage, the faster you're going to dry your hair, or the faster you're going to microwave your popcorn. They're going to use more energy every second. Okay. Let's suppose that it takes 10 minutes to dry your hair. How much energy will you use in 10 minutes? Well, the first thing you do is remember that 10 minutes is in minutes and we need seconds. 10 minutes is 600 seconds. So the energy, which is equal to the power times the time, is 1200 watts or joules per second times 600 seconds. 6 times 12 is 72, and there are 4 zeros. So about 720,000 joules. That seems like a lot of energy, but honestly, a joule is a very, very small amount of energy. So it's really not that much energy. Okay. I want to talk just a little bit more about electrical dangers and safeties, just while we're thinking about it. One of the things that we need to understand is that human beings are electrical machines. When you've all had that muscle twitch, well, that's an electrical signal. I can move my hand because my brain, my nervous system are sending electrical impulses telling me what to do. My heart beats because of electrical impulse. I can use an electric shock to start the heart, but they also often use a shock to actually start somebody's heart beating again. Because of that, we just have to be really careful around electricity. Even currents as small as 50 milliamps, which is a pretty small current, that can stop a beating heart. So when you're working with electricity, you just need to be cautious. If things say high voltage, believe them. Now, if we were in the lab and we were working with batteries, you're not going to hurt yourself with a 1.5 volt battery, but you can really hurt yourself with a 12 volt car battery. And one of the things that you may or may not have is that voltage in itself is not nearly as dangerous as the actual current. It's the current that flows through people that causes such severe damage. If you get struck by lightning, you could have a current as big as 25 amps flowing through. That's huge. So where electricity is concerned, just be cautious. Okay, we're going to do one more video over chapter 21. The second video is going to deal with circuits, in particular looking really close at series and parallel circuits and how things in those circuits behave.